This is the video lesson for torque and static equilibrium. The essential questions for this lesson are, what is static equilibrium, and how do we calculate the forces on objects in static equilibrium? So what is static equilibrium? So an object is said to be in static equilibrium if there is no net force and no net torque acting on the object. So, in other words, all forces cancel out. So, the sum of forces in the x direction equals 0. The sum of forces in the y direction equals 0. And all the torques cancel out. So, the sum of torques equals 0. So, we can see from this diagram of the seesaw, the little boy is less massive than the little girl. His mass is less than the little girl's mass, but he's sitting further out on the seesaw than she is. So if we multiply the force of gravity for the little boy times the radius from the central pivot point, his torque is going to be the same as her torque because her force is a little bit larger, but her radius is a little bit smaller. So the sum of their torques is going to be the same. Sum of their torques is going to be 0. So therefore, they are in static equilibrium. Okay, let's work example number 1. So you weigh 500 newtons at the edge of a 6-meter long seesaw with a weight of 200 newtons. How much force must the fulcrum supply to support you and your 700 Newton friend? Okay, so we can do this part of the problem with just our usual sum of forces in the y direction. So we have sum of forces in the y direction. So we've got you're the mass 1. So we have 500 newtons. Those are pointing down. That's pointing down, so it's negative. Then we have the fulcrum. We'll call that FP. So FP is positive, and that is 200 newtons. Then we have the fulcrum itself. So let's see, the 200 newtons is the weight of the seesaw. Then we have the fulcrum. So the 200 newtons is negative, actually. So negative 200 plus the force that the fulcrum is pushing up. So that's P for pivot. And then minus 700 newtons. And that's for the second person. That's for her mass 2. And that is all equal to 0 because none of this is moving. So combining like terms, you have minus 500, minus 200, that's minus 700, and then minus another 700, that's minus 1400. So the force that the pivot or the fulcrum is supporting is 1400 newtons. And just to clarify, this minus 200 newtons here, this is the mass of the seesaw itself. So the mass of the seesaw is 200 newtons, or that's the weight of the seesaw is 200 newtons, and its mass is calculated at the center of mass of the seesaw, which is in the middle of it. Okay, so this is example number 1 continued. So how far from the middle of the seesaw must your friend sit to balance the seesaw? Okay, so a couple of things to consider here. So when using the sum of torques equals 0, we want to choose the most convenient point to calculate the torques about. And secondly, the fulcrum and the seesaw's weight produce no torque about point A. So we're going to call this point A. So choosing that point will make the equations easier. All right, so let's bring some information over from the last slide. So the little boy weighs 500 newtons. So weight 1 is 500 newtons. Weight 2, that's little girl, is 700 newtons. And then the seesaw itself is 200 newtons. And the distance, total R, is 6 meters. Okay, so with our sum of torques, we have the little boy is 3 meters from the pivot point. So we're going to do 3 meters times 500 newtons, and then we have sine of 90 degrees because the weight is perpendicular to the axis of rotation, so that's equal to 1. And he is rotating the seesaw in a counterclockwise direction, so he's positive. Then the little girl would be rotating in a clockwise direction, so she's negative, so there's the negative sign. And we don't know how far she is, so she's X. Then she weighs 700 newtons, and she is again also, her masses, or her weight is perpendicular to the axis of rotation, so she ends up as 1. So we have, and this is all equal to 0. So we're going to simplify. I'm going to multiply 3 times 500, so that's 1500 Newton meters, and I'm going to move X times 700 newtons to the right side of the equation. So we have 700 newtons times X. So divide 1500 Newton meters by 700 newtons, and that gives us a distance from the pivot point to the little girl as being 2.1 meters from the pivot point. So this distance here, from here to here, F2 it says, is 2.1 meters. Okay, example 2. A 50 kilogram weight is attached to a 1 meter long bar supported by a cable attached to the wall as shown. If the bar has a mass of 50 kilograms, what is the tension in the cable? And then what force does the wall exert? Okay, so we've got several things we want to try and figure out here. So the first thing we want to do is figure out the force the wall exerts, or the first thing we're going to write equations for is the force the wall exerts. So we're talking about this point right here. So what force does the wall exert? So I'm going to draw a diagram. It's not exactly the same as a free body diagram, but it's pretty close. Okay, so here we have the force of the weight. Actually, let's change that from W to, change that from W to, we'll call that the mass. And that is 50 times 10, so M times G. So we'll call that 500 newtons. And then the bar itself has mass. It weighs 50 kilograms. So the FB, it's the same thing, 50 kilograms times 10 newtons per kilogram. So that's also going to be 500 newtons. And this distance from here to here is half a meter. So that is 0.5 meters. And then this distance from here, from here to here, from the wall to the end of the bar is 1 meter. Okay, and then we have our cable here with a 30-degree and this is tension. Okay, so we have this force. So we have the force of the wall. So the force of the wall in the y direction and the force of the wall in the x direction. So up here, I'm going to write our forces. So we have the force of the wall in the x direction. So let's do sum of forces in the x direction is equal to the force of the wall in the x direction. The only two forces working in the x direction are the force of the wall in the x direction and the tension force in the x direction. So the force of the wall in the x direction is positive because it's pointing to the right, and the force of the tension in the x direction is negative because it's pointing to the left, and add together those forces are 0. And then we have the sum of forces in the y direction. So that has more forces. So we have the force of wall in the y direction, we have the force of tension in the y direction, and then we have the force of the bar and the force of the hanging mass. So we've got all of those forces. So I'm going to do sum of forces in the y direction is equal to, so we have the force of the wall in the y direction plus the force of the tension force. So we have the tension force in the y direction. Those are positive. Then we have minus the force of the bar minus the force of the hanging mass. And that's all equal to 0 because this is all static. Nothing is moving. Okay. Now, so these are our equations set up. So here we can say that the force of the wall in the x direction is equal to the tension in the x direction. And here we can say that the force of the wall in the y direction is equal to the force of the bar minus plus the force of the hanging mass minus the tension in the y direction. Okay, now we're going to have to look at the sum of the torques to be able to figure out some of this information. Now we have the force of the bar, we have the force of the mass, hanging mass, but we don't have the tension in the y direction. We're going to have to use sum of torques to figure that out. So we have sum of the torques is equal to, now we're going to use this pivot point, so we can ignore that point. So we have, first we have 0.5 meters to our first force, which is 500 newtons. And this force, the force of the bar pulling downward, it would make a clockwise movement. So it's going to be negative. So minus 0.5 meters times 500 newtons, and then times sine of 90, because the force is working perpendicular to the axis of rotation. So that is equal to 1. Then we have another negative force, which is the hanging mass here. So the hanging mass is going to make the bar move in a clockwise position. So we have, it's all the way out at 1 meter times 500 newtons. And it is also working at a 90-degree angle. So that's also 1. Then plus we have the tension force. So the tension force is acting at 1 meter. And it is T. We don't know what the tension force is. And it has a sine of 30 degrees, which is not 1. Okay, and all that equals 0. Okay, so I'm going to simplify our sum of torques and move some things around. So on the left side, we have, so sine of 30 is 0.5. So we have 0.5 times T, and that's equal to, we have 0.5 times 500, so that is 250 Newton meters. Plus another 500 Newton meters. Kind of bleeding into this section here. Okay, so let's keep going down here. So we have 0.5 times T is equal to 750 Newton meters. So then our tension force is equal to 1,500 Newton meters. Okay, so I'm going to move some of this important information to another blank screen, and we will start from there. Okay, so I've got our information moved over. So in the last slide, at the end, I said that the tension was 1,500 Newton meters. It's actually just newtons because it is a force. So tension is, we figured out, is 1,500 newtons. The force of the bar is 500 newtons. So that's 50 kilograms times 100 or times 10 newtons per kilogram. And then the force of the hanging mass is 500 newtons. Theta, that's the angle between the bar and the cable that's keeping it held up. Our equation for the weight in the x direction, or for the wall, the force on the wall, so that's this force here, so that's Fwx, is equal to the tension in the x direction, and then the force on the wall in the y direction is equal to the force of the bar itself plus the force of the mass minus the tension in the y direction. Okay, so let's figure out the force of the wall in the x direction is equal to Tx, which is, so Tx is this component right here. So if we have, so here's our tension force. So this angle is 30 degrees. So Tx is right here. So it's equal to T cosine of 30. And then this is Ty, which is equal to T sine of 30. So T cosine of 30 is equal to 1,500 newtons times cosine of 30, which is equal to, so that's equal to 1,299 newtons. And then our force of the wall in the y direction is equal to, again, that's the force of the bar itself, that's 500 newtons, plus the force of the hanging mass, that's 500 newtons, minus, we have 1,500 newtons times sine of 30. So that equals total 250 newtons. So the answers to this problem are: the tension force is 1,500 newtons. The force on the wall in the x direction is 1,299 newtons, and the force on the wall in the y direction is 250 newtons. All right, let's look at example number 3. So we have a 4.5 meter long board with a mass of 10 kilograms. So the board itself has a mass of 10 kilograms and is supported by 2 sawhorses at points A and B. A 40 kilogram mass is hung from the board at 1 meter, so 1 meter from the left edge, and an 80 kilogram mass is hung 1.5 meters from the right edge. All right, so we want to find the force applied to the board by each sawhorse. Okay, so let's look at a note here. So this note says that the sum of forces in the y direction equals 0 gives us 2 unknowns. So it's going to give us A and B. So it's going to give us both A and B, but only one equation. So we'll have to use the sum of torques equals 0 to give us another equation that's going to allow us to solve for both A and B. So the sum of torques is going to give us B, and then we can plug in the answer to B to our answer that we got for the sum of forces in the y direction, and that will enable us to get A. Okay, so let's set up a free body diagram here so that we can look at all of our forces. Okay, so we have force A is pushing upward. The force of the mass A, let's call this mass A. So we'll call this weight A, and this is hanging down, and that is equal to 400 kilograms, or 400 newtons rather, sorry. So it's 40 kilograms times 10 newtons per kilogram, and this distance from here is 1 meter. Then we have the weight of the board itself. So the weight of the board hanging down is 10 kilograms times 100 times 10 kilograms per newton. So this is the weight of the board, and that's equal to 100 newtons. And this is in the middle of the board. So the middle of the board, this distance from here to here is 2.25 meters. So remember that something like a board, we have to account for its mass, and the board's mass is we counted at the center of mass, which is in the middle of the board, which in this case is, for a 4.5 meter long board, it's 2.25 meters. Then we have weight C, and that's 80 kilograms. So that's going to have a force of a weight of 80 newtons, or 800 newtons, sorry. And this distance here, so this distance from the edge, so it's 1.5 meters from the right edge. So it is going to have a distance of 3 meters from the left edge. And then finally we have this last force, which is force, we're calling it force B. So we have force A, that's the sawhorse. We have weight A, weight B, weight C, and then we have force B. Okay, so we're going to use the sum of forces in the y direction equals 0 to start us off. So sum of forces in the y direction equals, so we have force A is positive, minus weight A, which is 400 newtons, minus weight B, which is the weight of the board, minus weight C, which is the hexagon, which is the trapezoid looking weight, plus the force of the second sawhorse pushing upward. So first sawhorse and second sawhorse are both positive, all the other forces are negative, and that is equal to 0. Okay, so let's go ahead and solve this for A and B. So we have A plus B is equal to, so that's 1,300 newtons. So now we see we have one equation with two variables. So now we have to do the sum of torques to give us another equation that will allow us to solve for one of these two equations. So we're going to use A as the pivot point. So we can ignore force A. We can ignore the sawhorse A because it's the pivot point. So now all we need to do is look at the mass, the weight A, so the circular hanging weight, the weight of the board itself, and then the mass of the trapezoid hanging down. Okay, so we have sum of torques equal to, okay, so the mass A, it is 1 meter from the edge, so its radius is 1 meter. The mass itself is 400 kilograms, or 400 newtons. Okay, now notice that if this is the pivot point, mass A, or weight A, is going to cause a clockwise rotation. So this should be a negative, okay? And it is causing a rotation as perpendicular to the axis of rotation, so it would be a sine of 90, which is 1. So the next thing that we have to calculate is the weight of the board itself, weight B. It's also causing a clockwise rotation. So it would be at 2.25 meters, so 2.25 meters. And it weighs 100 newtons. It's also at 90 degrees to the axis of rotation, so it's equal to 1. Then finally next we have the trapezoid-shaped weight, which is 800 newtons. So it is 3 meters from the left edge, 3 meters from the pivot point. So we have 3 meters, it's 800 newtons. And it is also at 90 degrees to the axis of rotation. So that's a 1. And then finally we have plus, and we have at 4.5 meters, because it's all the way at the edge, we have force B, and it's sine of 90. Running out of space here. Sine of 90, which is a 1. Okay, so let's simplify all this. Okay, so 1 times 400 is 400. 2.25 times 100 is 225. 3 times 800 is 240. And then, so those are all negative. So we have 400, 225, 240. Let's see. This is all equal to 0. So our sum of forces then, we have FB times 4.5 meters is equal to 3,025 Newton meters. Okay, so I'm going to move our important information. This equation, these two equations, FA plus FB equals 1,300 newtons, and then 4.5 meters times FB equals 3,025 Newton meters to another screen. Okay, so to find our force B, we have to divide both sides by 4.5 meters. So force B then is equal to 672 newtons. So using that amount of force into the first equation, FA plus FB equals 1,300 newtons, we have FA plus 672 newtons is equal to 1,300 newtons. That gives us FA is equal to 628 newtons. So the sawhorse on the far right side, force B, is holding up 627 newtons worth of weight. And then force A, the sawhorse on the left side, is holding up 628 newtons worth of weight. Okay, example 4. Last example. We have a 3 meter long ladder with a mass of 20 kilograms, leans up against a frictionless wall, and makes a 50-degree angle with the ground. What is the force exerted on the wall by the ladder? And then what friction and normal forces are exerted by the ground? Okay, so let's draw a diagram here. So here's our ladder. Okay, so we have our normal force against the wall here. This angle is 50 degrees. So that's perpendicular there. Okay. Then we have, this is the friction force. And then this force is our normal force 2. So this is the normal force against the ground. This is the friction force. And then we have the weight of the ladder. So this is FG. And this angle here, since this makes a right triangle, and this is 50 degrees, this angle here has to be 40 degrees. Okay, so let's look at our forces here. So let's do sum of forces in the x direction and y direction. So sum of forces in the x direction, the only forces in the x direction we have are the normal force, so Fn1, so that's going in the positive direction. And then the friction force is actually pointing in this direction because the ladder is trying to move in this direction. So the friction force is opposing it. So minus the force of friction, and that's equal to 0. So our normal force, Fn1, is equal to our friction force. All right, let's look at our forces in the y direction. So in the y direction, we have our normal force 2, that's the force of the ground, minus Fg, that's the force of the ladder pulling down, and that's equal to 0. So sum of forces, we have the normal force of the ground pushing against the ladder is equal to the force of gravity. And we know what that is. The ladder has a mass of 20 kilograms, so 20 times 10 newtons per kilogram. That gives us a force on the ladder of 200 newtons. So the normal force of the ladder on the ground is 200 newtons. Okay, now we have to use our sum of torques. Okay, so we're going to use this as our pivot point. So starting with the normal force, so this force is pushing in this, so the normal force from the wall at the top is pushing in this direction. So that's clockwise, so that would be a negative force. So we have minus 3 meters times Fn1, and that is at a 50-degree angle, so sine of 50. Then we have the force of the ladder pulling down, so that's moving it in a positive direction, a counterclockwise direction. So that's plus, and that is at 1.5 meters from the pivot point. So that's 1.5 meters. And we know that that force is 200 newtons. So that's 200 newtons, and that is at an angle of 40 degrees. So that's sine of 40 degrees, and that all equals 0. So let's do some simplification here and solve for Fn1. So simplifying and moving stuff around, we have 192.8 Newton meters is equal to 3 meters times sine of 50 times Fn1. So then Fn1 is equal to 83.9 newtons. And so since Fn1 is equal to friction, we can say that the friction force is equal to 83.9 newtons. So the friction force of friction is 83.9 newtons. So friction is 83.9 newtons, and the normal force exerted by the ground is 200 newtons. That's how you solve this problem.